What's up, physics crew? We are going to talk about the period and frequency of a mass spring system, and to do this we will look at circular motion because we've said multiple times that they're really closely tied. It's just that the circular motion is 2D, whereas simple harmonic motion is usually 1D. So consider the energy transfer in a mass spring system where you're going from all kinetic at equilibrium to the potential in the spring where you might hit the lowest point. Our expression would be written out 1/2 mv squared equals 1/2 kx squared. We know the 1/2s cancel out. And here's what might need a little bit of time to wrap your mind around. I'm going to define my v to be 2 pi r over t. And this expression comes from uniform circular motion. If I go back over to my phase diagram, I could see that, well, here's my low point and here's my high point of this oscillating mass. And on the circle, my low point would be here, and my high point in the brown dot would be right here. And this would be 2x, right? This x would be a displacement, this x would be a displacement. So the overall diameter would be 2x, which means the radius of this circle is x. So in this definition that velocity is 2 pi r over t, I'm saying that the radius is x based on the close tie of circular motion to simple harmonic motion. So in this case, I get 2 pi, and by the way, we're making the simplification of circular motion to simple harmonic motion because to derive this actual expression that we're after involves some calculus. So do try and get your head around how we're making that definition and simplification to this situation. So we substitute v in, we see that the x's should cancel out, and I'm left with that expression. I will, let's see, take the t squared and move it to the other side. Meanwhile, multiplying m over here and dividing by k, so I get something that looks like this. I take the square root of both sides because I want to get rid of that t squared part. So I get the period of a spring is equal to 2 pi times the square root of the mass of the block that's on the spring over k, the spring constant. And to figure out the frequency, well, it's really quite easy because I know the frequency is the inverse of the period. So I could do 1 over that entire expression to get the frequency. Notice that the period is not dependent on how far the spring is stretched. So if I stretch something out further, it will have the same period as if I only stretch it a little bit. Now, that might be hard to believe, so I need to try and prove it as best I can with experiment. So here I go. I'm going to turn on this projector. And the experiment is one that I'm using with AlgoDo, as I have done most of this lecture series, because I can easily eliminate friction. Alright, let's see, I'm going to need to move this over once my browser pops up. Okay, let's see AlgoDo. Beautiful. So here's my block, this is frictionless, and my stretched out spring. Now let's let this thing go for a little bit, just to get an idea of what's happening. Okay, so it seems to be oscillating between somewhere like that and somewhere like that point. I guess I could move that a bit further out. Okay, so those are my oscillation points roughly. Now I'm going to try and time it, and I'm going to time 3 cycles. So here I go. When it gets back here, I'm going to start timing it. Go. And I know that there's going to be some error. That's 1. That's 2. So I should account for some sort of error. Alright, so 3 cycles got me 10.72. I hope you can see that, 10.72 seconds. So the theory goes that if I were to stretch this thing out, now before I do that, let me dampen this so that we get to equilibrium. If I stretch this thing out further, so all I really need to do is push this thing in to a position. Oh, that's not what I wanted to do. I'm going to push this thing in. Whoa, that was fun. Alright. Now I should get something similar to 10.72 when I do all of this. Let me remove the damping. If that happens, then physics works. If it doesn't, then let's reconsider the laws of physics. Whoa! That's nuts. Okay. Well, that was very interesting. I guess this program takes some getting used to, so I'm getting used to that I don't fully have down. But, will that work? Ah, that seems to work. Okay. So now I need to redefine my new max and min. I'm going to say that point and that point. I got my max down. My min is a little bit shorter. Something like that. Okay. That's my best approximation. Now 10.72 is what we're aiming for in 3 complete cycles. So when it gets back here, I'm going to start timing it. Bam. There's 1 cycle. 2 cycles. And 3 cycles. 10.67. Physics works. There's a little bit of difference, but that is so close. I hope you can believe me that how far you stretch this spring has no effect on the period, the time it takes to complete a revolution. That's all for now, folks. Thanks for sticking with me in the troubles and of algo do, and I hope you learned some physics.